Hi everyone. Alright, so this is the video for activity 9.1 where we're looking at a two-factor ANOVA. And in this example we have two different independent variables. One is drug A versus B. That is, are people taking drug A or drug B? And the other independent variable is gender, male or female. And then we're looking at, as our dependent variable, memory scores. Okay, so we want to know is drug A or B more effective in improving memory, right? And then also are there gender differences in memory? And then also, are those two drugs differently effective for men and women? Okay, so I already have the data file pulled up here. You'll notice that I have already labeled drugs A and B. In your data file, when you download it, it'll just say 1 and 2, and you can change those by clicking on the drug A label here. Okay. Same thing, you can change gender. They're coded so that 1 is equal to male, 2 equals female, and you can change those as well. Okay. All right, so we're going to run an ANOVA by putting both independent variables in the fixed factor box. Right? A factor is another word for an independent variable. Memory score is my dependent variable. Okay. And you can see that your ANOVA is being computed for you as you move the variables over into the boxes. Okay, so we're going to start by looking at the interaction. So the interaction between gender and drugs. Okay. So in order to do this, let's start by doing a couple of things. One is click on additional options. Okay. And we're going to get estimates of effect size and get omega squared. So we're going to look at omega squared as our effect size. You can also get partial eta squared if you like, but we're going to focus on omega squared. So I'm going to delete that partial eta squared there. Now let's also look at a graph, right? So click on descriptive plots, and we're going to look at a graph of these two independent variables simultaneously. So I'm going to put drug A versus B on the horizontal axis and make separate lines for gender. Okay. And it's by default giving me the confidence intervals there, but if that didn't happen for you, click on display error bars and then ask for the confidence intervals. Okay. All right, so this is the main information we need to get started looking at our interaction. Right? So when we look at our interaction, we're looking at up here in your ANOVA summary table, you're looking at gender by drug. Okay? Looking at the gender by drug interaction. Okay? And here we have an F that has 1 in 136 degrees of freedom. So the degrees of freedom 1 are right here, and 136 are the residual degrees of freedom. The F is equal to 15.98, and that gives us a P of 0.0001, right? Which means that our interaction is unlikely to be due to sampling error here. Right? So what do we mean by having an interaction? Right? So an interaction means that the effect of drug A versus drug B on memory scores depends on whether or not you're male or female. Okay? So if you look at the graph here, if we look at males, we can see that males have better memory scores with drug A than with drug B. Females had better memory scores with drug B than with drug A. Right? So it's an interaction because different things are happening for the males and females. Okay. So if we look here, you see your descriptive statistics are in the table above, right? The graphs are a nice visual display, but they're not very precise. You get the exact means and standard deviations for males and females there. Okay. Now what we want to know is, for males, is there a difference between drug A and drug B that's unlikely to be due to sampling error? So this difference is between 19.72 and 16.73. We want to know, is that difference likely to be due to sampling error? Or in our graphs, we're looking at, for males, are these 2 points here different from each other? Or is that difference likely to be due to sampling error? We also want to look at for females. So for females, is this difference between 16.2 with drug A and 19.05 with drug B likely to be due to sampling error? Right? So it looks like females have higher memory scores with drug B than drug A, but it's possible that that's due to sampling error. All right, so to investigate this, we're going to do simple effects analyses. Okay, so if you click on the menu for simple main effects here on the left-hand side, right, and we're going to look at the simple effect for males and females. So I'm putting gender as my moderator factor, and simple effect factor is drug A or B. Okay, and then you're going to get a table like this one here that says simple main effects. All right, so what this table is doing is we have the simple main effects for males, right? And the F there is 8.39 with a P of 0.004. Right? That means that the P for the comparison between 19.72 and 16.73, right? These two means for males, the P is 0.004. So that difference is very unlikely to be due to sampling error. For females, now we're comparing 16.21 and 19.05 and find that the P for that comparison is 0.0066, right? So that also shows us that the difference for females is unlikely to be due to sampling error. Right? But note that something different happened for males and females, right? Both of their differences are unlikely to be due to sampling error. But what's really important to note here is that for males, they had higher memory scores with drug A than with drug B, and for females, they had higher memory scores with drug B than drug A. So when you describe the interaction, you don't just talk about how low the p-value is, right? But you're also talking about the overall size of the difference there. So I'm not going to compute effect sizes here. You can do D's by hand, and to compute effect size D's by hand, you can just take for any two means you're comparing, like for males, you compare 19.7 and 16.7. Your numerator is 19.7 minus 16.7. And then you can just take the average of the two standard deviations. Because our sample sizes are equal, it works to just take the average of the two standard deviations. Alternatively, you could use an online calculator to find the D there as well. Okay, but we're not going to do that right now. All right, so we have our interaction, and that's really the most interesting finding here, and that is that males did better with drug A than drug B, females did better with drug B than with drug A. Okay, but we also want to look at the main effects. Right? And so the main effects are looking at the effect of one independent variable all by itself on the dependent measure. Okay. All right, so if we look at starting with gender, if you look back at the ANOVA summary table at the top, gender, right, has an F of 0.66, right, with a P of 0.42. Right? So that tells us that the differences that we would observe overall between males and females are very unlikely to be due to sampling error. Now, if we take a look at the additional options, under marginal means, you can move gender over into the box. Right. You see for marginal means, it shows us that the overall mean for males is 18.22. The overall mean for females is 17.66. Right? And the p-value for the main effect of gender tells us that that difference we're observing is unlikely to be due to sampling error. Right? Note right now we're just ignoring drug A versus drug B. So the difference between those two is likely to be due to sampling error. So likely due to sampling error because the P is 0.42. Okay. Now we can also look at the main effect for drug A versus B. So now I'm going to move drug A versus B. Sorry, I would do that. Move drug A versus B over into the right-hand box for marginal means. And now we're comparing the mean of 17.97 and 17.89. And the P for that main effect of drug A versus B is 0.92. So very likely to be just due to sampling error. So for both of these main effects, we're ignoring the other factor at this point, or averaging across them. So if for example, the male mean is 18.22, which is just the average of the two means for the men. For females, the average is 17.63, which is just the average of the two means for females. For drug A versus B, you're looking at the average of drug A. So that's the average of the means for males and females with drug A. And the average for B is just the average for males and females for drug B. Usually the main effects aren't as interesting as the interaction. The reason you're doing a factorial ANOVA is usually because the interaction is what's most interesting for the analyses that you're going to do. So I haven't done every single thing that's in the activity for you. You'll still be doing some computations of effect sizes by hand, but this will get you through getting the analyses through JASP and also finding the values that you're going to use to answer those questions. Okay. All right. Good luck with the activity.